Okay, so off we go. So last time we just barely kind of got started talking about dot products. This is a topic y'all presumably seen before in some form or another. Remember, dot products are the model for inner products, right? And I know that some Math219 instructors like to take sort of an inner product point of view, and that's fine. But in this course, there's really no reason to maintain that sort of generality. Where the only inner product we're going to use in this entire course is the regular old Euclidean dot product, like so. That formula, and I'm going to use that notation because it's so handy. Dot, right? About as easy as it could get. Okay, make sure you're good with all the properties listed in the book and in your linear algebra book as well. I do want to talk a little bit about the language of the related concepts of perpendicularity and orthogonality. A lot of books and a lot of instructors kind of conflate these two things. Math's pretty much the same idea. A lot of people don't even realize that they're different. But very importantly, there really is a difference here. Because on the one hand, there's this what I like to call geometric idea of perpendicularity. I think perpendicularity is a natural word here. And that is in reference to the geometric trait of a vector as having a direction. Right? You can talk about two vectors and the two directions that they define and the angle between those two directions. Now that's all geometry, right? Directions and angles, it's all geometry, right? So this is a geometric idea, and it only makes sense for non-zero vectors, right? What direction does the zero vector point? It doesn't really point in a direction, right? So it just makes no sense to talk about the zero vector as being perpendicular to something. It's nonsense. Right. Now, here is a very closely related idea, to be fair. This is what I'm going to call an algebraic concept. You can talk about the case, the scenario in which you have two vectors whose dot product is zero. Now, yeah, I know, it's very closely related to perpendicularity, right? But it's not the exact same thing, because this little scenario, where two vectors have a dot product equal to zero, either or both could totally be zero, and this makes perfect sense. Right? So these ideas apply to different collections of vectors. They are different sort of, you might say, turf, right? One is about geometry, one is about algebra. Dot product is an algebraic construction. An equation is an algebraic construction, right? So I think it's important to keep these two ideas distinct from each other. And we have the perfect tools for keeping these ideas distinct from each other. And that is that we have two words that we can, two ideas, two words, we can pair them up and make sure to use the right word for the right concept. Right. Now, that said, I will confess, I was not brought up right on this point. I was brought up mathematically, that is, being, pretty much using the word orthogonal as kind of a $5 word for a 50-cent concept of perpendicularity. Right, fancy talk for perpendicular. And so I make mistakes on this, more than I wish I did. Thinking perpendicular, but I say orthogonal or vice versa. So when you get it drilled into you at a young age, and then, after 10 years of having it drilled into you, you start to realize, hey, this is not good. It's really hard to break that habit. And I'm working on it. I'm doing my best. Likewise for y'all. So do your best on that. Okay, here's a really cool idea. If you have a non-zero vector, v, surprisingly often we want to find the unique unit vector that points in the same direction. And there's a really easy formula. There it is. All you got to do is take the non-zero vector in question and divide it by its own magnitude. Super easy. It's a not particularly challenging, but nevertheless worthwhile exercise to think through why this is true. Right? Take this vector that this formula for this vector u, compute its magnitude, confirm that you get 1. No big deal, but like I said, give it a try. Okay, handy dandy formula. Make sure that you're good with that formula. We're going to be using it a lot. Next idea, component. This is a useful concept. Sometimes we have some vector that we're interested in, say W, representing something. My favorite metaphor for this is a football game, and in this little hypothetical football game, the ball started here, and then something happened, a play happened, and then the ball went there. And how many yards of gain was that play in football? Well, it's not this. It's not however many yards that is. The magnitude of that vector does not tell us the yardage gain, because you don't get credit for a first down by throwing the ball 10 yards sideways, right? All that matters in football is how far have you gone downfield. Right? That's all that matters. So in this scenario, we don't care about that blue vector. We only care about this orange scalar. Very importantly, this is a scalar. It's now I'm going to do my best to resist calling this a distance. It feels like a distance, and sometimes it even is a distance. But the problem there is distances are intrinsically positive things. A component does not have to be positive. If the W vector were pointing this way, then the component would be negative. AKA, if you sack the quarterback, that's a loss. That's negative yardage, yes.
It's the same idea as like projections.
Very closely related, but importantly different. We'll talk about that in a couple seconds.
Okay.
Yeah. So, so it's a scalar. It's kind of like a distance, but importantly not exactly. Okay, now all of this said, how are we actually going to compute this component? And this is a pretty straightforward calculation. You can, and by the way, this is assuming that our direction that we're interested in is described by some vector v. And so altogether, the big idea is to notice that this is a right triangle, and y'all know trig, right? So think it through, right? There's the trig of that triangle. That's how cosine works. And y'all are good at manipulating trig. Read that. Make sure that you follow all those details. Good exercise. As always, ask me if you have any questions. And here's our final formula. And let's see if I can get all this onto the same page. Here we go. Yeah. So the component, namely that, is computed by that formula right there. So it's a good formula to know. By the way, this is not a formula that I memorize. I never have memorized this in my life for a good reason that I'll tell you momentarily. There's an alternative I prefer, and that comes from noticing as follows here, that we have v divided by its own magnitude, which, as we just discussed, is the unit vector pointing in the same direction as v. So if we simply replace, v divided by the magnitude of v with, what it is. I mean, in fact, that's the unit vector pointing in that direction. Then our formula for component simplifies really nicely. Instead of having to think of component as, well, it's the dot product of the given vector with the direction vector and then divided by the magnitude of, okay, that's a lot. It doesn't roll off the tongue very nicely, right? We get a much crisper little formula right here. Components are dot products with unit vectors, right? Pithy, tight, right? I think that's really appealing. And so this is how I understand components, and this is how I've always computed components, and this is the formula that I've memorized. Because it's so easy, right? Very often when you do things naturally, they become easier. So I think this is both natural and easier. So, okay, there you go. All right, now related idea. Somebody asked about projection. It is a very closely related idea. Again, we have some vector. Again, we have a direction, and that is the only direction in which I actually care about the given vector. Again, I have some vector defining that direction. And again, I'm going to be looking at what one might loosely call that side of this triangle. The big difference is that the projection is a vector. It's not a scalar. Component's a scalar. Right? Projection is the vector itself. That is, you might say that W, the initial vector W, is literally the sum of the vector that is the projection plus this other vector over here, which you might call the orthogonal component or something like that. All right. So how are we going to get our hands on that? Now, again, there are different ways that you can approach this. I'm going to show you what I think is the most natural, ultimately simplest way to think about it. And that is, as is very often the case, it's easiest to think about this vector in terms of its direction and its magnitude. I mean, that's fundamentally what vectors are, direction and magnitude, right? So, the direction that points is very easy to write down. It points in the direction that is the unit vector. It points in the direction of the V that defines the direction we were talking about in the first place. It's very natural to represent directions with unit vectors. And now what's the magnitude? Right? What's the what is it that I multiplied by, and now I'm going to have to sweep a little subtlety under the rug here, and I always feel guilty about this, but I'm going to want to call the magnitude the component. Because again, look at this. It's the scalar that's kind of telling you in some sense how big this vector is, and that sounds great until you remember magnitudes are always positive. Magnitude is an intrinsically positive thing. Component is not. Component could be negative. Well, it turns out that's kind of perfect, because if the W vector were pointing back that way, I'd want the projection to be back that way also. So in fact, the component is exactly what we need. It accounts for the magnitude, and it accounts for the fact that the projection might be going the other way. So, perfect. Everybody good? So, nice and simple. The projection, its direction is a intuitively satisfying thing. Its magnitude, again, apologies, air quotes, its magnitude also intuitively satisfying thing. Its component, as previously discussed. So this, I think, is the most natural formula to remember. I couldn't forget this if I tried. It just makes sense, right? And then, conveniently as well, we have an easy formula for component already. Remember, we talked about that on the last page. And so altogether, this is the formula for projection that I strongly encourage. I think that's the formula that makes the most sense. All right, now there is another formula, and I am going to talk you through this other formula. It's no big deal. It's just a recognition that this unit vector here is something that we have an easy formula for. You just plug that in, move things around a little bit. Fun and games with dot products and magnitudes, right? Again, make sure you check those. Check the algebra, make sure you're good with that. And notice that the result is this alternative formula for projection. And a lot of students like this second formula. And let me first play devil's advocate and talk about what I like about this formula. This formula says that if you are asked to compute a projection, and you're given an object vector and a direction vector. You got the W and the V given, and then this formula is in terms of W and V, and it's very plug and chug friendly. And that's appealing. And not really what this course is about, right? So again, this, this is how I can do the stuff that this course isn't concerned with is not the strongest pitch, really, right? So on the other hand, again, thinking about this course is about ideas and understanding and connecting ideas to other ideas. What's the idea behind, why is this obvious? I don't think it is. I don't think it's obvious at all. I think this is obvious up here. I think this is really satisfying intuitively. This is transparent as to why this is true. This is the result of a detailed punching up of algebra. So conceptually, I'm a fan of that one, and I'm kind of on that one. Again, I don't hate it. Look, if I were taking this course, if I were an undergrad in this course, I would memorize both. Right? Because, there might be a time on the exam when you have to punch something up super quickly, and this might save you, 30 seconds or 15 seconds. That might matter, I suppose, right? But what are you going to remember 10 years from now? This one. And possibly as soon as a month from now, you're going to be trying to remember, wait a minute, it's a dot product divided by a dot, which do I dot with what, and which one's on top and which one's on the bottom, right? This is a formula of details that doesn't really, you can't rederive this easily without that. All right. Okay, last comment on 1.3. The book has some nice examples of how you can use vector algebra to do certain proofs in plane geometry. This is pretty straight read. It's not even real. It's linear algebra, really. It's not really multivariable calculus. So you might not have seen these kinds of proofs in your linear algebra class, but it only really uses, I'm going to call it easy linear algebra. So do please take an example. They take a read, to the two nice examples that they have in the book. Think about how they do the setups. That's really the hardest part of these kinds of exercises. Is to think through, make good decisions about how you're going to set things. How are you going to label with vectors aspects of the geometry of the problem at hand? And then from that, it's just a matter of writing down vector algebra. Good examples to read through, and I think there's at least one homework exercise that's in this direction. Whoops. There we go. Okay, moving along. 1.4. Let's talk about cross products. There are a bunch of things to say about cross product. Two things I want to comment before we get into the details. One is, this is one of the sections where I've had to make what I would say the most tough choices of things that I wish I had time to talk about, but I just don't. Right? And again, there's too much material in this class. I just can't get it all done, and so in some cases, there's stuff I have to leave to y'all to, read the book on your own. And of course, every class does that. Some are a little bit more and a little bit less transparent about it. So some things we will have to leave you to read on your own. The stuff in this section, some of the stuff anyway in this section that I need to leave you to read on your own, is sufficiently non-trivial that I don't really feel comfortable holding you responsible for it if I'm not going to talk about it in class. And I wish I could, because this is super fun. Matt, there's some really cool ideas in here. Beautiful mathematical ideas. So, tough choices. I just can't spend the time. So there's a fair amount of stuff here in the notes that I'm going to draw a big red X through, and you are not responsible for it. Right? Now that said, it doesn't mean it's not useful. is still cool. It still might help you understand the stuff you are responsible for. So I still encourage you to look at it. You don't have to. There won't be any test questions on that stuff that I'm about to X out. But I mean, if you're looking to help yourself understand that the proofs that I'm going to X out are neato and helpful, and I encourage you to look at them. Okay. Oh, yeah. Second thing I want to say, there are lots of different connections between a lot of different ideas in this section. It's this is not a sort of like, this and then that and then that and then that and then that and that's the story. It's more of a kind of a hairball of connections of everything connects to everything else in all sorts of complicated different ways. So how one goes through all of those ideas there's a million options on how to do that. So I'm going to show you the order through these ideas that I think is the most natural, the most transparent, the most geometrically satisfying, the most intuitive. It is not the most rigorous. And I am going to have a gaping hole of rigor in the presentation I'm going to give you. And this is Math219, not 222, so that's okay. Right. Okay. So anyway, FYI. So you may notice that the order that I'm going to present these ideas is different from the order that the book does. That's why I think you're going to like mine better. This is just an opinion, right? But I really think you will. The book gets a little hairy in a few places, and mine won't. Okay, here we go. So we're going to start off by talking about what we mean by clockwise and counterclockwise lists of two vectors in R2. Okay, so first of all, what do I mean by a list? So a list is kind of like a set, but very importantly, a list is ordered. So when I say A and B, I listed first A. That means A is importantly and intrinsically to the list first. This is not arbitrary, right? A is first, B is second, because I wrote it down that way. Okay. All right. So what do I mean by clockwise and counterclockwise? Well, if you have a list, A first, B second, I'm going to represent that by this arrow indicating which order we go through there. Well, the first vector, A, perhaps like that. The second vector, B, let's suppose B is like that. Notice if you go through this list, A first, B second, and then you come over here and ask, okay, well, if I go from the direction that A is pointing to the direction that B is pointing, notice I'm rotating counterclockwise. Right? So I'm going to call this, given this A and B, I'm going to call this a counterclockwise list because of that picture. Everybody okay? All right. Now, hypothetically, let's suppose I was talking about different vectors, also called A and B. So A is still first, B is still second. But now let's suppose that A is that vector. That's the first vector. And B, the second vector, is this. Now, what would I call that? Well, again, A first, B second. Pretty reasonable to call that clockwise. Is that cool? Yeah.
So do you just assume to go like the shortest distance rather than like all the way around?
Yeah, that's right. That's right, exactly. Yeah. And then, of course, there are some cases where it doesn't really make sense either way. So, for example, here's A, here's B. You don't really have to turn at all, or you could say you do a full turn, but you could just as well do a full turn in either direction. It is not clear whether we should call this clockwise or counterclockwise. By the way, there's other versions of this. What if the A pointed the exact opposite of the direction of B? Or what if one or both of these vectors was 0, then we got nothing. And you'll notice pretty quickly that the cases that couldn't reasonably be called either clockwise or counterclockwise are all linearly dependent. That's a cute little observation, I think. So these are your three scenarios. This based on this idea of again what I'm calling the geometric order of a list. The options are counterclockwise, clockwise, and dependent. Okay. All right. Now, real quick, this is all pretty satisfying, I think, but there are some nice properties you can notice of this idea of geometric order of a list. First of all, they're mirror images of each other, right? Counterclockwise and clockwise are reflections of each other. Look in the mirror and look at a clock, it's going the wrong way. Okay. Second, if you put the vectors in the opposite order, if you trade the positions of those two vectors, notice A comma B is counterclockwise, but when I trade B comma A, it becomes clockwise. Same two vectors, but trading the positions changes the order. And then lastly, if you take the whole picture, right here I have A and B, and that list A comma B is clearly counterclockwise. If you take this whole picture here, just grab this whole thing and just rotate the entire story, it's still counterclockwise. Right? Rotating the whole picture doesn't change the picture. And my real world version of this is if you look at a clock, which I guess is behind everybody, but if you look at a clock, right, you can see which way the minute hand goes. If you turn your head to the side, it's still going the same direction, right? That rotating everything doesn't really change anything. All right. Okay. Natural next question. Can we do something like this in 3 dimensions? And yep. We can still talk about an ordered list. 3 vectors in R3, 3 vectors in space. Right? And let's see here. Well, I don't have clocks that are 3-dimensional like that, so we can't literally do clockwise, counterclockwise, but there's a fantastically analogous alternative, and that's what I'm going to call right-handed and left-handed. Okay, again, in reference to the list. And here's the idea. Start with your right hand. There's a particular gesture that we do. Somebody made it up. It's arbitrary, but it's pretty standard. And that's this move right here, this gesture right here. So the rules to this gesture: index parallel to your palm, right? Index finger parallel to your palm. Middle finger's bending the natural way. I know that you could probably do that, but that's not what we're doing here, right? So natural, comfortable bending of the middle finger. Thumb, again, you could probably grab that thumb and hoist it around various different directions, but don't. So kind of like this, right? This list of vectors right here, I've got A, B, C. A first, B second, C third. I can point A, my index finger in the direction of A. I can point my middle finger in the direction of B. And sure enough, my thumb is pointing pretty much in the same direction as C. I'm going to call this a right-hand ordering. And then I'm going to refine this point a little bit to recognize that A and B define a plane. And even if I can't get my thumb to point exactly in the direction of C, right? Maybe I'm not quite that flexible. What I can do is point out that, look, C points on one side or the other side of that plane. And we don't need our thumb to point exactly in the direction of C. All we need is for our thumb to point on the same side of the plane as C. Is that cool? You want A and B, yes. You want to be able to do that with your fingers, right? But as long as C is on the same side of the plane as your thumb, you're all good. Okay, so this trio ABC, this list ABC for those vectors is right-handed. Now let's ask the question. Let's not look at the answer here. just yet, right? Let's ask, what about if these were A, B, C? And again, still looking at the same list. A first, B second, C third. Is this right-handed? And look, I can point my index finger in the direction of A. And I can actually point my middle finger in the direction of B as well. I just have to kind of negotiate my hand around to a different arrangement. And yeah, A in the direction of, index in the direction of the first vector, middle finger in the direction of the second vector. And now unavoidably my thumb is pointing on the wrong side of the plane compared to C. So this is not a right-handed list, but it's a left-handed list. Anybody see what I mean? So again, it's kind of, it has certain features in common with clockwise, counterclockwise. They're kind of, two different versions. One, if one works, the other doesn't, like that. And then there are, of course, the anomalous, sort of annoying, what if C is not on either side of the plane? What if it's parallel to that same plane defined by A and B? What if one of the vectors is 0? Right. All those sort of failures of the previously discussed system, they're all linearly dependent. Okay. All right, so that's kind of the three-dimensional version of clockwise, counterclockwise. By the way, totally awesome. It's got all the same properties. Right and left hands are mirror images of each other. Right? If you trade two of the vectors, you change the order. Now, let's sort of think this through. A first, B second, C third is right-handed. But if I do B first, A second, C third, that's left-handed. And this will always work. Whenever you take any list, if you switch the position of any two of the vectors in the list, the handedness changes. Okay. And then lastly, it's independent of rotations. And again, this is a pretty easy pitch. That's a right hand. This is the human right hand. And if I rotate every vector, it is still a human right hand. Right? So I think that's likewise a pretty easy one to buy. Now there is no sort of two-dimensional version of this fourth property. I think this is really nice to observe. It's what we call cycling the list. Cycling means that we're going to take every vector, its position in the list, and sort of move it over by one. Every vector, move it over by one. This vector here, I can't move it over by one. It kind of falls off, so I bring it back and put it in the position that was recently vacated by the other. So that's what we call cycling. And neat fact, cycling preserves the order. And this is another sort of lovely hand-waving geometric proof. Here's what cycling looks like geometrically. It's this move right here. And this is a nice one to think through, right? Take a minute, actually do this move. Notice in both cases, my three fingers are pointing in those three directions, but different finger for each vector because I do this little gesture. Right? And this is effectively the same as cycling. So again, preserves handedness. Okay. All right. So, next thing. Y'all may have probably seen some version of this theorem in linear algebra. You almost certainly saw some version of this in linear algebra. I also suspect you probably did not see at least some of this in linear algebra. And I think this is a really big deal. This is one of my, I think kind of cornerstone point of view on all the arguments that we're about to make here. And this, by the way, is where I am going to sweep rigor under the rug. And so I'm going to state this theorem. I'm going to assert it. I'm not going to prove it. I'm aware of two ways to prove these theorems that I'm about to show you. One of them is a little too sophisticated for Math219. It's not that we couldn't do it, it's that it would take an hour, and ultimately it's mostly defining things, and it's not really, ultimately not that deep if you get right down to it. So it's sophisticated but time consuming. It's just not appropriate in this class. If this were Math 531, I would totally show you. It would take 5 minutes. It's not that big a deal. The other proof that I'm aware of is tedious and detail heavy and unnecessarily unwieldy and clunky and lots of machinery that just doesn't need to be there. Right? There's a much better proof out there. So anyway, I just don't think it makes sense to prove this theorem in a class like this. So again, I'm just going to assert this and not prove it. Okay, so here's what the theorem says. By the way, what the theorem says is not currently on the screen. What we have on the screen is just setup. The actual conclusion of this theorem is what I'm about to scroll down to in a moment. But the setup is a little bit involved, so let's do the setup first. Notice we start with a list. Oh, let me get back into the better mode here. We start with a list. By the way, this is 2 vectors in R2. Now, if you give me a list, I can make a matrix in a pretty natural way. First vector becomes the first column. Second vector becomes the second column. That's pretty natural, I think. So if you give me a list, effectively, you've kind of implied a matrix. Okay. Well, it is also true, if you give me a matrix, that implies a linear transformation, right, by way of that formula, the usual, the natural formula relating a matrix to a linear transformation. So now let's a little bit weird. You gave me a list, and from that I infer a matrix and a linear transformation. And then I'm going to further infer, that sounds weird, by looking at the unit square. Right, I've got this linear transformation that came from the givens. I've got a linear transformation. I can look at the unit square and I can see what is the resulting image. And that image is going to be a parallelogram, and that's a fact of linear algebra. And again, a good exercise for those of you who are looking to remind yourself of, if you want a little linear algebra practice, how would you show that the image of any rectangle by way of a linear transformation, the result would be some form of a parallelogram. Something to think about. Okay, so lots of resulting objects, right? So we've got a list, a matrix, a linear transformation, and a parallelogram. 4 separate objects, but they're all kind of the same thing. They all come from the same thing. Everybody on board so far? Yeah.
Wait, so what is as defined as? So like
the unit square.
Okay.
Yeah, so 0 to 1, 0 to 1. Yeah, totally.
So like in that case it'd be like 1, 1, right?
This point up here is 1, 1. That's right.
Okay, so but you're putting it into like the function t, right? So
Yeah. So what I mean by this sort of picture here is this is the domain and this is the resulting image. Right. Yeah, totally. Okay, so here's the theorem, and again, I think y'all have probably seen at least some version of this. If you look at the determinant, specifically at the absolute value of the determinant of that matrix, that will compute the area of this parallelogram. Show of hands, how many people have seen that before? Okay, most. That's cool. Cool. Now here's a different point of view on this. Different point of view. We've related the determinant of this to the area of this. But what does that have to do with the linear transformation? What does the determinant tell me about the linear transformation? It actually tells me something really important about the linear transformation. Because after all, the linear transformation turns the unit square into that parallelogram. The linear transformation turns an area of 1 into an area which is the determinant. The linear transformation magnifies areas by the determinant. And that's another really important interpretation that very often gets left out when you're talking about this theorem, sort of a first-time take on this theorem. So I don't know, different contexts call for different interpretations, but I think there's a case to be made that arguably the most natural way to think about the magnitude of the determinant is that it's an area stretching factor. It's how much does this guy stretch out areas? No square necessary, no parallelogram necessary. It describes a process, not a picture. And in different situations, that can actually be really, really useful. So there's that. Okay, the other thing that we can learn about these objects concerns the sign of the determinant. Plus or minus. I claim it's going to actually tell me the order of the list, which is really surprising. I mean, most of the time, if you think about it, what would be your guess as to how you would determine whether a list of two vectors is clockwise or counterclockwise? Well, you'd probably say, well, I guess I'd better draw those vectors and then kind of look at the page and measure that angle or something and just visually see from the directions that they point whether it's clockwise or counterclockwise. And I'm saying you don't have to. I'm saying you can take your list, make a matrix, take the determinant, see if it's plus or minus. That tells you the answer. Plus means counterclockwise. Minus means clockwise. So that's pretty surprising. What does this tell us about the linear transformation? Again, very often swept under the rug the first time discussing this result. Now I'm going to make a couple of observations here. Silly, obvious observation is that being E1 and that being E2. Notice E1, E2 is clearly counterclockwise. I'm just going to, you know what, I've got a big mess. Let me just do this. E1, E2, clearly counterclockwise. Now let's look at the images. Now the image of E1, y'all remember the rule, right? The images of the standard basis vectors are always the columns. The columns, of course, are the vectors in the list. The vectors in the list, as I'm sure you've noticed, are A and B. They are the edges of the parallelogram. So that's the image of E1. That's the image of E2. And notice, as I have it drawn here, also counterclockwise. So one way to say what we interpret, let's start by thinking about when the determinant's positive. If the determinant's positive, this is counterclockwise as drawn. You could stop there. You could say, well, counterclockwise, sure. It also means, though, that counterclockwise turned into counterclockwise. It means that handedness order was preserved. And now let's think about how you preserve these orders, right? What kinds of linear transformations would preserve order? Magnifications will turn counterclockwise into counterclockwise. Rotations will turn counterclockwise into counterclockwise. Shearing transformations will turn counterclockwise into counterclockwise. But flips will not. Right? Geometric appeal. If there is any sort of a flip, reflection, however you want to say it, anything that turns the plane upside down, as it were, will not turn counterclockwise into counterclockwise. It would turn counterclockwise into clockwise. So this is a really nice interpretation. The sign of the determinant not only tells you about the order, it tells you about the transformation and whether the transformation has a flip hidden inside of it somewhere. Right? And again, typically something that you would think that you would have to kind of look at the geometry and see how you'd have to understand in some sense how a lot about the transformation and what it does and think about it geometrically. Nope. Look at this determinant. Plus means no flip. Minus means there's a flip. Everybody happy? Right. Okay. Cool stuff. This looks like the exact same theorem, doesn't it? I did this on purpose. I deliberately wrote this theorem, laid out on the page exactly the same way, because it's morally the same result. It's, 3 vectors now instead of 2. It's in 3 dimensions instead of 2. It's a 3 by 3 matrix instead of 2 by 2. Et cetera, et cetera. It's a parallelepiped instead of a parallelogram. Oh, gosh. There we go. It's got volume instead of area. Totally analogous. Copycat. If you had to guess what the result of this theorem would be, you would guess correctly. The list gives us a matrix, gives us a transformation, gives us a parallelepiped. The magnitude of the determinant gives us the volume. Seems like a reasonable guess, and it's true. And the sign of the determinant tells us whether there is some sort of an inversion inside of here. Is there a reflection hidden inside of this linear transformation or not? Said differently, does the intrinsically right-hand order E1, E2, E3 turn into a right-handed order list of images? Or does the right-handed E1, E2, E3 turn into a left-handed list of images? All determined by the determinant. Hey, maybe that's why they call it. Is that cool? Everybody happy? All right. So, good stuff. Let's see. Moving along now. Here's where I really am going to take some liberties with the order that the book has presented these ideas. Again, look, the book makes a perfectly reasonable case. By the way, I love our book. It's a really good book. Excellent book. That said, I have my own opinions about a lot of things. This happens in probably every math class. Your instructors are always going to have opinions a little different from that of the author. So she does it her way, I do it my way. So here's the definition of cross product, and it's a weird and unnatural looking formula at a first glance. I encourage you not to memorize this formula. I think it's weird looking, and I would never be able to keep it straight. I would mess up a minus sign. Oh my God, there's 6 different ways that I could mess up the minus signs. What are the odds that I'm going to get all 6 correct? Not good. Not for me, right? So here's what I think is a much easier formula, and that is that the cross product is this, what we call symbolic determinant. I have to call it a symbolic determinant because I can't really quite call it a real determinant, because a real determinant is something you do to a matrix. A matrix has as its elements scalars. This, whatever that thing is, has a vector as an element. That's weird. You're not really supposed to do it. That's not a thing, right? That ain't right. You know what I mean? Okay, so it's not a real matrix, and so this is not a real determinant, but if you kind of sweep that under the rug and just kind of ignore that and just kind of, I'm just going to go ahead and use our usual formula. The usual formula where you go across the top row and plus, minus, plus, all that business, cofactors, etc. It will compute exactly the right formula. So this is what I memorize. It's really easy to memorize. It's got patterns, right? I don't have to remember a bunch of minus signs. I've already memorized those minus signs when I had to memorize the formula for determinant. So, might as well piggyback off of that existing knowledge. Okay. Let's see here. And, I think we are out of time here. So I guess we have to draw the line right here. We'll pick up here next time. See y'all later. Have a great weekend.
Thank you.
Yep.